Let me now define what is a finite extension. L is said to be a finite extension of K if it is a finite dimensional K vector space. Well, the dimension of L over K is called the degree of the extension. Is called degree of L over K, and it's denoted as follows: L over K. Let me prove a theorem. Suppose L is an extension of K and M is an extension of L. Then M is finite over K if and only if M is finite over L and L is finite over K. Moreover, in this case, the degrees multiply. The degree of M over K is a product of the degree of M over L and the degree of L over K. Well, let me prove this theorem for you. One direction, suppose M is finite over K. Well, any family of elements of M which are linearly independent over L, of course, is linearly independent over K. Any M1 and so on, Mn, which are independent over L, are also linearly independent over K. This is obvious because what is linear independence? This is non-existence of linear combinations with coefficients from L or from K, which is 0. Of course, if there is no such combination with L coefficients, a fortiori, there is no such combination with K coefficients because K is a subfield of L, is a part of L. So, thus, the dimension of M over L is finite, because you cannot have a linearly independent family of more than dimension of M over K elements. Well, now, on the other hand, L is a K vector subspace of M. So if M is finite dimensional over K, then L is also finite dimensional over K, since a subspace of a finite dimensional vector space is also a finite dimension. So one direction is easy. The other direction is also easy, but one must make a little computation. So let E1 and so on En be an L basis of M, and let epsilon 1 and so on epsilon G be a K basis of L. So let us prove that EI epsilon J form a K basis of M. Well, indeed, any X from M is a linear combination of EI with L coefficients. X is a sum of AI, EI, with AI in L. Well, each AI is also a linear combination, let's say sum of Bij of epsilon j, where the Bij are from K this time. So we can write X as a sum by over I and j over Bij epsilon j EI. So that is to say that epsilon j EI, which is of course the same thing as EI epsilon j, generate M over K. And we only have to check that these are linearly independent over K. So on the other hand, if we have some linear combination over I and j, Cij EI epsilon j, if this should be 0, then of course we can recompose the terms. Then we have a sum over I, a sum over j, Cij epsilon j, EI is 0, but EI, so these coefficients are in L, right? But EI form a basis, so for any I, the sum of Cij epsilon j is 0, but this means as epsilon j form a basis that Cij is 0 for all I and j. So theorem 1 is proved. Now I would like to prove a second theorem. Let me introduce one more notation, which is quite obvious. I will call K alpha 1 and so on, alpha n in L, the smallest subfield of L containing K and the alpha I. I will also often say that this is generated by alpha 1, and so on, alpha n is generated by alpha 1 and so on, alpha n over k. So this is smallest subfield containing k and alpha I. So theorem 2. L is finite over k if and only if L is generated by a finite number of algebraic elements over k. Well, again, one direction is obvious. If L is a finite dimensional k-vector space, then we can take a basis. Let alpha 1 and so on alpha d be a k-basis of L. Then L is certainly equal to the smallest subring of L containing alpha 1 and so on alpha d, which is a field, so it's also the smallest subfield of L containing alpha 1 and so on alpha d. Now all alpha I are algebraic. This is just because, well, moreover, each k alpha I is a finite dimensional k algebra. Since it is a subring of L, which is already finite dimensional. So then by proposition 1, alpha I is algebraic. Well, in the other direction, it is also not difficult. We have k alpha 1 is finite dimensional over k alpha 1 alpha 2 is finite dimensional over k alpha 1 and so on, k alpha 1 and so on alpha d is finite dimensional over k alpha 1 and so on alpha d minus 1. So all of those elements are algebraic, so all of those guys are fields, k alpha 1 and so on alpha I is a field, so it's equal to k of alpha 1 and so on alpha I. And now just use theorem 1 to conclude that L, which is k of alpha 1 and so on alpha d, is finite over k.